Hello everyone, welcome to an algebra video tutorial. We are getting an introduction to exponential functions. We've been going through geometric sequences and looking at patterns in number sequences where we multiply repeatedly to get the next term. But we're going to broaden that out and now start to look at exponential functions. Hopefully we've got a good foundation. You'll see a lot of similarities to geometric sequences as we define exponential functions. So here we go. We've got a geometric sequence starting with the number 3, then 6, 12, 24, 48. You can probably tell that the pattern is we're multiplying by 2 repeatedly. 6 times 2 gives you 12. 12 times 2 gives you 24. 24 times 2 gives you 48, and so on. And previously, in working with geometric sequences, we saw that we needed a starting value. We always had the first term, which in this case was 3. And then we had what was called the common ratio. If I divide consecutive terms in a geometric sequence, they always should equal the same thing. And that was the number that we actually multiply by. And the formula, if you remember, repeated multiplication, any term in a geometric sequence, a sub n, is equal to the first term, so we got to start somewhere, but then I'm multiplying by a whole bunch of my common ratios, multiplying by a whole bunch of r's. We use r in general, and then we did the n minus 1 power. We had to know how many r's am I multiplying by, and it was just easier to use exponents. So in this particular example, the equation would be, or the formula would be a sub n equals 3 times 2 to the n minus 1 power. That's what we've been learning. And when we did the graph was points, disconnected points. So the graph of disconnected points. So we could plot every point, but notice every term is only first term, second term, third term. There's no 1 3/8 term or 2.99 term. So you can't connect all the dots if we're just graphing the geometric sequence. All right, let's leave that behind now. I'm going to draw a big purple line. That's everything about geometric, and we're done with geometric. We are ready to get into exponential functions. So exponential functions, I'm going to write it out here. An exponential function always has this form. F of x equals a times b, we use the parentheses, so a times b to the x power. All right, so what does this mean? It looks sort of similar to the formula we have over here, right, for geometric sequences. But let's break the things down here. A, when we're talking about A is our starting value. It's the same thing as the starting value for geometric sequence. So starting value. But specifically in exponential functions, A has to be greater than 0. We can't have a be 0 because then you get kind of some weird stuff with multiplying by 0, and you can't have a be a negative value because then technically it's not an exponential function. So we're going to set a as a starting value, and a has to be a number greater than 0. Okay, b. B is called the base, but it is essentially the same thing as the common ratio. B is that number we're multiplying by. That's why it's got the exponent for x. So b is my base. It's what we're repeatedly multiplying by. And b, guess what? B also has to be greater than 0. I can't have b be negative. It's kind of an interesting function, but it's not an exponential function. So b has to be greater than 0, and b can't equal 1. If b is 1, then I just have some value a times 1 repeatedly, and I actually don't have any function. I just have a constant value. So b can't be 1 because that's not very interesting to multiply by 1. And b has to be positive because I can't be flip-flopping with negative values and taking powers of negative values. So there we go. We've defined a, we've defined b. X is my independent variable in the exponent. Independent variable. And f of x is my output, or we get our, or we get our y back for our dependent variable. So we're going to still use x's and y's. Let me spell dependent right. Dependent variable. All right, and there we are. And so if I wanted to model this particular function, I would say, okay, I could either use f of x, write it in function notation, equals 3 times 2 to the x power, or I could write it in not function notation form and say y equals 3 times 2 to the x power. Just be comfortable with both of them. But this function would contain these values for x is 1, 2, 3, 4. But the nice thing is I can use any values in here now. So I could put 1.35 in for x, calculate that, and see what I get back for y. I can put anything I want to in for x, calculate it, and get it back for y. So if I was to graph the graph of an exponential function is a smooth curve. We're going to do a lot more with graphs as we get onto this series as well. But there you go. We've defined what our exponential function is. Really similar to geometric sequences. We're starting with a value, repeatedly multiplying by some number over and over again. So just fitting that pattern of what we've been working with. But it's exponential because my input variable, my independent variable, is being put in directly into the exponent. So we get some interesting things happen with exponential functions. All right, stay tuned. We'll be working a lot with money, with population growth, with radioactive decay. We'll be looking a lot at graphs and functions and connecting how the graph looks with the actual equation and really digging in to understand how exponential functions work.